Right. So, over the page. This set of notes. Okay. Whether we get through everything today will be a little bit of trial and error. But fundamental electrical quantities. Ohm's law, power calculations, which we've already done in science, so we shouldn't take too long on that. Series and parallel combination resistance, we've done in science. Solving basic circuit problems, that in science, Ohm's law and that kind of thing. Voltage and current dividers, again we've touched on that in science. Kirchoff. First practical, let's sort of round orientate to some of the practical we're going to do. Also a way of doing a practical where you confirm that a circuit complies with Kirchoff's voltage and current laws. Right, by doing the calculations first, then building the circuit and taking some measurements and comparing what you measure practically with place and confirming that within experimental error those circuits conform to those laws. Yep. So, fundamental electrical quantities. Charge. So electricity moves along a conductor in the form of charge. The electrons basically move. So if we've got a piece of copper that we're zoomed in on, part of a piece of cable made from copper, a copper atom has got its nucleus, and then it's got several shells of electrons. But the outside shell, I don't want to go too much into the chemistry, but the outside shell of electrons has only got one electron in it, and that's some distance from the positive charge of the nucleus. Because it's some distance away, it makes it a good conductor because we can encourage those electrons to jump ship. So if we got a load of copper atoms in here, still writing in the proper place, with their associated electrons spinning around the outside. This is without any added battery or voltage at the moment. Yeah. But if we connect a battery to that, plus and minus, like so, remembering that the whole part of that conductor is copper, this positive charge here will attract this electron to jump ship and go up back. That makes that copper atom there overall positively charged because it's got one electron less than it has protons. So it's attractive to this electron which jumps ship and goes onto that atom. And this one jumps ship and goes on there. And so on all the way through. These electrons jump from one copper atom to the other. That's the flow of electricity. When we say tensional current from positive to negative, the actual electron flow is in the opposite direction. That's the only time I will ever say or talk about electron flow. But actual electrons flow there, but we always have this convention, and certainly in my classes, that current flows from positive to negative. And you think about the holes that are left behind moving instead of the electrons. Alright, so when a jump ship that leaves a hole behind on the copper atom before, so holes are moving in the opposite direction. Actual current flow, a single electron will be moving about this speed. When the electron moves this end, all move. All the same, just a constant. It's like water through a pipe. Yeah. The unit of charge is a coulomb, and 1 coulomb is 6.24 times 10 to the 18, so lots of electrons. All right. We'll come across charge again when we look at capacitors as well, because then we'll want to measure the charge on 2 plates of a capacitor. So coulombs will come up then. But we're not going to get too heavily charged in terms of here. All you want to know is that that's around the current flow in a circuit. So charging coulombs we can calculate from Q is equal to pi times T. So that is the amount of flow times the amount of seconds. There's an example calculation there, and I've already done it in the notes, so I don't want to spend too long on that. But if a current of 5 amps flows for 2 minutes, the grounded charge flowing is 650. Everyone happy with that so far? So that's new. We didn't cover that in science. Voltage. We did cover voltage in science. Voltages are the pressure. It's the quantity that pushes current in the circuit. So it forces those electrons to think of it as being like the pressure of a pump. If you like stuff. So the voltage is like the pressure from your pump. It forces current around the circuit. There are a couple of names. Call it potential difference. So that's the difference between 2 different points on a circuit in volts, or an EMF, which is, you'd use EMF for a source like a battery or a voltage from a generator. Okay, so in terms of, if we have a circuit, simple series circuit, a battery, a potential difference is like the voltage you would measure if you put your meter between any 2 points around the circuit. So you'd have a potential difference across that pair of resistors. It's a different potential difference between there and there. Here, technically, we're measuring an EMF because that's a source of electromotive force. But all of them are measured in volts. You also hear me use the volt drop across R3. Yeah, same thing. All measured in volts. Okay? If there's no difference, you won't get a current flow. So if this point here is at 12 volts and that point is at 12 volts, no current flow. There has to be a difference. One has to be higher than the other. It's like having a tank and another tank. They've got to be at different levels for water to flow between them, unless you pump it. Okay, and then you're creating a difference anyway. All right? Yeah? All happy? Good. Current. This is a measure of the rate at which charge flows. We've already seen that in the bit about charge. Okay. It's designated by the symbol I, and that's measured in amperes. And the current will flow depending on the other things. So it will depend on how much voltage you apply and how much resistance there is in the circuit. Because as you already know, we covered in science, resistance, electrical circuit, is the opposition to current flow. And that's all this relationship with Ohm's law, where if you put the resistance up, keeping the voltage the same, the current will go down. Put the resistance down, the current will go up. Alternatively, increase voltage, current goes up. Decrease voltage, current goes down. So that's that Ohm's law relationship. All right? All parts of a real circuit must have some kind of resistance to flow. Without it, we would not convert electrical energy into some other form, heat, light, motion, etc. Yeah. Everyone happy with that? Again, revision from science. So I'll put it in your notes for completeness. Unit multiples and submultiples, so you've got them to hand for this module. So you're fairly familiar now with using the multiples of 1,000 for kilo, mega as a million, giga as 1,000 million, and the submultiples, milli, micro, nano, and pico. And if you look at the last two, and remember they're in alphabetical order, you won't get the nano and pico the wrong way around. You're going to come across them mainly when we look at capacitance, because the farad is such a big unit compared to what you actually achieve. Okay, and there's that important note there that when you use these quantities, several different quantities in a formula like Ohm's law, they must all be either in the base multiple or all in the same multiple, or use the multiples to convert between them. So you have to be a bit careful. If you mix, you can't mix milliamps in the same formula unless you use the power of 10 notation. Alright, but you're all happy with that, aren't you? Any dissenting voices? So, Ohm's law. Again, we've covered this in science, but it's in the electrical principles notes as well. Relationship, it's the relationship between the applied voltage, the resistance, and the current flowing. And I always say the current last because the current happens because of the other two. We control the current by playing around with the voltage or with the resistance. It's a consequence of the other two. Right? We might have a power supply that says we can set the current, but what we're actually doing is changing the voltage so that the current changes. Alright? So where V is the applied voltage, I is the current flowing in amps, R is resistance, we have Ohm's law, I is equal to V over R. You can rearrange that to the three different versions. Again, you're fairly conversed with that from science, I hope. Yep. Please say if you don't get any of this. Because Ohm's law, if you study with me to the end of level 6, you'll still be using Ohm's law in 3 years' time. That never goes wrong. Alright? Power. This is the rate at which energy, measured in joules, is being used. In electrical terms, it's the rate at which electrical energy is converted to some other form. That be light, heat, rotational motion, etc. So we have 3 different formulae for power, and that's worthwhile remembering them all. Appropriate one according to the information you've been given. So we've got power is the current times the voltage. If you have Ohm's law and that formula, you can do every kind of 4 variable thing. If you know 2, you can find the other 2, except it's much better to know the other 2 and use the appropriate one with the information you've been given. So we also have P is equal to I squared R, commonly used by engineers who want to make it so complicated as it is. They talk about I squared R losses instead of just saying power. Everybody would understand. And then have your P is equal to B squared divided by R. Depending on the question, you can use one of those 3. And if you look on the internet, you'll find some, like circular diagrams where all the formula, depending on the two things you've been given, all the rearranged formulas have been given. I leave you to find one of them for yourselves if you think that would be helpful. All right, that's like a wheel. What do you want to find? You know P and I. This formula will give you V. That formula will give you R, and so on. All right. The note at the bottom, Ohm's law, formulae for power given, so far is absolutely fundamental to the study of electrical science. You'll get nowhere without it, and you should be committing those formulae to memory. Certainly, if you had exams, I wouldn't be putting those formulae on the formula sheet. That's fundamental to every electrical person's ability to be able to remember those. All right? Example problem. Find the voltage required to be applied to the circuit of resistance 15 ohms to make a current of 3 amps flow through the circuit. Also calculate the power dissipated in the resistor. Where are we going to start? Yeah, so the formula we're going to use, first of all, what do we know? Voltage is a question mark. So that's what we know. And where are we going with this? How are we going to make a start? Still no good. Yeah, that's 3 times 15, 45 volts. Yeah, you could do. Why might I not like that quite so much? Yeah, I mean, in this particular example, you've got an exact answer and you haven't rounded it. And you make a good point, either that or you've screwed it up. If you use, what formula could we use and only use the two pieces of information we've been given in the question? So let's change that to I squared R, which is 3 squared times 15. 135 watts. Yeah, have a go at the second question while I have another go at this one. Yeah, so we're trying to find here R equals B divided by I. Yeah, so that's 12 over, and there the important thing is that we do times 10 to the minus 3 with the current. Yep. The answer is 240 ohms. In the power, yeah, in this case, it is best to use because that's what we've been given in the question. So we're 12 times 50 times 10 to the minus 3 equals 0.6 watts, which is 600 milliwatts. Either would do in the answer to an assignment question, unless you were specifically asked otherwise. Yeah. Okay. So in your notes, there are, after that, well, there's an important note about good practice to use given values, which I've already talked about. And then there's some Ohm's law and power self-assessment questions. I'm going to leave you to use them as a revision. We've already been through. I don't want to labour on that too much because I know you're okay with Ohm's law, and we've been through it twice now already. Yeah, so they're there for you. And as always, the answer you should be getting is that value in square brackets. Yeah. Series resistance. Again, this is revision from science. However, I think, as always, there's a little bit of confusion pop up, or there's likelihood when we start talking about combination circuits. So we're going to go through the stuff again. So when we get series resistance, it's two resistors, for example, connected end on end. For any series connected, all in series, any number up to Rn, we just add them together. Sometimes you'll hear that called the equivalent resistance of, because what you're doing when you add R1 and R2 together, you're coming up with a single resistor, R12 we often call it, that would replace that in the circuit, and you'd still have the same current flow with the same voltage applied. Yeah. So that's what you're doing when you add those two together. You're finding that the total resistance of them, but that's also the equivalent. We could take two 10 ohm resistors in series out and put 120 in, and we'd have the same circuit. Yeah. We change nothing else. So series is fairly easy. Then we have parallel resistance. And we get resistors connected across each other, like that's shown in the figure. Okay. There's three methods for calculating total resistance of a parallel circuit. The first one is called the product over sum rule. That's where we've got two resistors only, and they can be of any value. And product means multiply. So we multiply the two values together on the top of the fraction, and we add the two values together on the bottom. Okay? And that'll come up quite regularly, this two resistor parallel network. And it's the quickest way to do that is to use product over sum. All right? However, if you get a question where you've got two resistors and you're given the total and the value of one of them, don't attempt to rearrange the product over sum formula. You'll probably get in a muddle. All right? I would recommend you use the next formula if you get that. So you want a total of 20 and you've got a 30. What other one do you put with it to get 20? I wouldn't try and rearrange this formula for R1 or R2. All right? If you've got three or more resistors, and they can be any value up to Rn resistors, the total resistance is 1 over the reciprocal of all the resistances added together. All right. Another useful way to write that, because most of the calculators I work with these days, certainly the Casio ones, the reciprocal button is x to the minus 1. So you put you put R1 to the minus 1, which is the same as 1 over R1, plus R1, 2 to the minus 1, R3 to the minus 1, all the way up to Rn to the minus 1. Put all of that in a set of brackets, and then take the reciprocal of the bracketed term. Okay? Either way, you should get the same answer. And then lastly, if you get a parallel combination where all the resistors in that combination are exactly the same value, for instance, if you have four 100 ohm resistors in parallel, the total resistance is 100 over 4. So value of each individual resistance divided by how many of them there are. Yeah. And the other thing, what's the other tip to remember about the total in terms of resistor parallel network? The tip about the total, the little check that you got the right answer. Yeah, the total is always lower than the lowest resistor in the parallel section. All right, but that's the total of that parallel bit, not necessarily the whole thing. Again, there's source of confusion there that we might crop up a bit later. Are you all okay with calculating series and parallel resistance as separate circuits? Yeah? Good. So, example problem. Resistor of 150 ohms connected in parallel with another of 75. Calculate the total. And the second problem, 33, 67 and 75 in parallel. Calculate the total. Have a go at that. Right, where are we going with the first one, boys? RT, product over sum. So R1 times R2 over R1 plus R2, that's 75 times 150 over 225 equals 50. And that fits in with our little rule that the total is lower than the smallest one, because our smallest is 75 and the total is 50. Yeah. Second one, how are we doing it? Do you want me to do one other or some more right? Yep, so that's the formula. Yeah. So we're 1 over, and that's 1 over 33 plus 1 over 67 plus 1 over 75. And the answer to that is 17.07 ohms. And again, that's lower than the smallest, which is 33. Yep. Okay, so that's series on its own, parallel on its own. Then we get to the point where times two different ways that we could have what's called a combination circuit, where we got both series and parallel. The first one, combination type A, is we've got one resistor in series with two other resistors that are parallel. Yeah. And then in the second basic type, we've got two resistors in series, and those two are in parallel with a third. Yeah. And there is, we could make up a formula for that one in one go. We could do R1 plus the product over sum formula for those two. We'll stay away from that bit, we'll have to eventually. But there's no direct formula really for that one. So the way to do it is, here we do parallel on this pair and end up with two resistors in series that we can add together. And on here we'd series up those two and do the parallel on that result of the other resistor, and again. Okay. So, example problem. Calculate the total resistance of that network. All the resistors are 100 ohms. started. So yeah, we got R1, R12 together. That's equal to R1 plus R2. So that's 100 plus 100 is 200. And the next thing, product over sum with R1 is R12 times R12 plus 2 times 100 over 200 plus 100 equals 66. I'm going to argue with you there. 0.7 because the 0.6 is recurrent. So what would I better put, thinking about what we were doing in maths this morning? If I want to keep all the accuracy. 6.7 or 6.6 recurrent is 2/3. Yeah, good enough to be able to think of that and do that. Keep that full accuracy, 66 and 2/3. All right. Next. Okay, so you got R1, 2, 3, 4 is R1, 2, 3 plus 4, which is 66 and 2/3 plus 100, 166 2/3. Much better you. Yeah. Is there a quick one? Remember that both 100? Yeah. So R45 is equal to R over 2. So 100 over 2 equals 58. Because they're both the same, they just half. Alright. Therefore, RT is R1, 2, 3, 4 plus R45. That is 166 and 2/3 plus 50 equals 216 and 2/3. Yep. Okay. But what I want to point out is this tool is not less than any of the parallel resistors. This parallel total is less than the 200 ohm resistors that are in parallel together. Yeah? And this parallel resistance is less than any of the two resistances that are in parallel together, 100 and 200. Just be careful. It's a little water. You've got to isolate that parallel bit to take it off. It's not the overall total because that's the total of the combination. So what we're saying is we can take all of that out and put one resistance of 216 and 2/3 ohms in the circuit. We'd have exactly the same circuit in terms of current given voltage. Yeah. You're all happy with that, and what you're doing is you've essentially broken that circuit down into all series because you've solved that bit by adding those two together in parallel. So you're taking all that out and put one resistor in. R4 is a series anyway. You've paralleled that up to give you one resistor. So effectively you've got three things in series to add all together to get the final answer. So that's what you're looking for if it's a combination. It's breaking it down until you end up with either all series or all parallel, and then you can use the formula. Alright everyone? Yeah. No dissenting voices? I'll move on. Series circuit. The voltage divider. Oh, this is a bit small. Again, I think we've probably covered this in the science. But if we apply voltage E to a series circuit, resistors R1 and R2, we'd have a volt drop across each resistor, V1 and V2. Alright? And the current I in the series circuit is a constant throughout because it only has one path to travel. So the key thing about current is there aren't any leaks. Every electron that leaves the terminal, or every positive charge that leaves this terminal, goes all the way round and comes back to that terminal. So it's the only thing where everything in your house leaves it and you still pay a bill for the privilege. Yeah. What it is, it divides that voltage up into two separate voltages. And we'll formalise that a little bit later on when we consider Kirchoff's law. But we can calculate the current by dividing the total voltage by RT. And as we know, RT is R1 plus R2. So we could write that the current is E over R1 plus R2. We don't really need a separate calculation to calculate the total resistance in this instance because the circuit is fairly simple. If that was that last circuit we looked at, you'd probably want to put it down a bit, calculate a total to get the current, and then do the individual things. But fairly simple. We've got V1 as I1, 1, 2 as I1 times R2. All okay with that? Yeah. So, looking at the example problem, if a supply voltage of 30 volts and two resistors are both 15 ohms, find the current I, and the voltage, which is V1 and V2. Yeah, RT. Yeah, 15 plus 15, 30 ohms. Yeah. One amp. Yeah. IR1 for the first one then, yeah. 1 times 15 equals 15 volts. Yeah, and VR2 is equal to I times R2, which is 1 times 15 equals 15 volts. Have you got on your page, calculate what happens if R1's changed to 10 ohms and R2's changed to 20? Well, can you do that, please? So change R1. E.g., RT still equal to 30 ohms. So the current is still an amp because we didn't change the voltage. Where? Oh, 20, yeah. It's part of my deliberate mistake. Current is still an amp because the total resistance stayed the same. The 2 volt resistors different. They still add up to the applied voltage E. Again, formalise that for we're Kirchoff's voltage law around anything. Alright? Yeah. So it divides up in the ratio of the resistances. Yeah. So if we went, what that means, if we went 100 ohms and 200 ohms, the current would be different, much less, but it would be a 10 volt, 20 volt split for the applied voltage or the volt drops across them, or 1,000 ohms and 2,000 ohms. Yeah. Current would change, but those two voltages would still split in the same way. Voltage divider, useful circuit. And we can consider the voltage divider in one go, really, by playing around with the formula a bit. We can get formula for calculating the volt drop across one of the two resistors in one go. We know that the total resistance is R1 plus R2, and therefore circuit current is I is equal to E over R1 plus R2, and the volt drop across a resistor V1, for instance, is I times R1. So we got equation 2 here. If we substitute I times R1 into there, we end up with E1 as E times R1 over R1 plus R2. Equally, so we can find the V1 voltage by multiplying the total voltage by, we can find drop across R2 by switching in 2 into there. So we can get that volt drop all in one go instead of separate equations. Okay? Usually in a question I won't care which way you do it unless you're specifically asked to use the voltage divider rule. Alright? Yep. Good. There are some questions there that will help you if you want to practice the calculation of voltages and currents in series circuits. Again, I'm not going to labour on that today because I think it's practical important to bring something to life and actually see all of this. Again, the answers to those are in the square brackets at the end of the question. So that's for you to prove that. Parallel circuits. Can't do it. I've got to when I'm done. When the components connected in parallel, okay, and that's all parallel only combination, then the drop across each of them is the same. What we're saying there is anywhere we go on this wire to that wire, measuring the same voltage we measure E. So a total current IT is drawn from the source, which divides into two currents, I1 and I2, joined back into IT the other side. All of that current must be somewhere, and it must end up back at the other terminal of the source. Alright, so what you'll hear these two currents called sometimes as leg currents, two parallel legs, calculate the leg currents, branch currents. Okay. They take parallel paths or legs. And again, I point out in the notes here that these two separate currents join up again after the branch form IT, because all the current leaving the source must return to them. Hence, for the power circuit, IT is I1 plus I2. Both resistors will have the same voltage across. So, in this particular instance, we can calculate I1 by dividing E by R1. We calculate 2 by dividing E by R2. Yep. All happy with the current divider. Example problem on the next page. Right, Taylor, how you done it then? What, onions, biscuits? Sorry? By the way, I have an adversity to words like amperage, so I don't want to hear that in my classes. 0.3 recurrent is I keep doing that now. A 0.5 and a third. Yeah, you can't do 0.5. That's kind of when it starts to come unstuck. You could have it as a fraction, because you'd have to do a half plus a third, which is what? 5, 6. Yes, yeah, because a third's 2, 6, yeah, 5, 6. So again, well, yeah, 5, 6. All right. I mean that rounding there won't matter in a final answer, but if you're using that current in another significant calculation, particularly if you're multiplying it by a big number, a high voltage in terms of calculating the power, then that could make a significant difference to using 5, 6. All right. So the other way you could have done it was calculate the total resistance. Yeah. Use that to calculate IT, and then calculate 2, and then there's a check that adds together the total. Right. So it actually work that way. A little tip down the pot before we start. Because in my answer I'm down, because most students tend to go down the total resistance, then separately find the two currents, and I say, yeah, you can check it by adding them together. So the tip down the bottom is equally as good to do what calculate the separate currents, and then add them together to get the... Alright? Again, are some example questions that you can have a go at. Right. At some point, we won't skip like this every week, but we've already kind of done this in science, so I'm trying to move things along a bit. Right. I know you spend loads of time at home practicing your calculations. Calculating current and voltage in combination circuit. Right. We're going to do this one together for the very reason that your practical circuit is quite close to this. Alright? So, when I give you the practical notes, what you're going to have to do initially is calculate all the values for the circuit and we in a table. And then when you've done that, and you're happy, or Jeff or I'm happy with that, then you can get your practical kit out and take your measurements to the computer. Right? So, where do we start with a circuit like this? Total resistance. Can we do that all in one go? You could do, and I think you probably might need the total of R2 and R3 at some point anyway. We'll go down that route. You could do it all in one go, because you can do R plus and do plus R4 and calculate the total all in one go. But I think we'll find we're going to need the total of these two to do that voltage anyway at some point. So R23 is equal to R2 times R3 over R1 plus R3. That is 6 times 18 over 24 equals 4.5 ohms. Therefore, RT is equal to R1 plus R23 plus R4, which is 2 plus 4.5 plus 15 equals 21.5 ohms. So, yeah, go on. Yep. Neither. Where did 10 volts come from? No. To calculate what? No. You're dividing a voltage by a resistance to get a voltage. Anything the law that you've learned. That's fine. I'm not trying to make a fool. That's a common mistake. Yeah. Okay. Common mistake. You'll all laugh. You'll all make one, including me. Right? Mine are deliberate, as you always know. Yeah. One thing I like to encourage you to do is write on things that you've found out. So this R23 is 4.5 ohms. Yeah. RT is 21.5. Now, with what we now know, what can we calculate? Now that we've found out RT, what can we calculate? Yeah, we can calculate the total current, because what we've effectively said is we've got a circuit, we can replace this with our 20 volts and one resistor of 21.5 ohms, and we'd have the same circuit, remember. So we can calculate this IT. IT is E over RT 20 over 21.5 equals 0.93 amperes. So again, do it in green, nice and calculate the value, 0.93 amps. Yeah. Now what can we do, Reed? Tell me how to do it then. Yeah, all of that current is going through that resistor. We can use an Ohm's law, we can find the volt drop or the potential difference across that resistor. We can isolate that. We know two things about it. We can find the third. We could even well find because we know the current and the resistance as well, if we wanted to. So we can find V1. V1 or VR1, I'll call it V1. It's V1 on the diagram, isn't it? Is equal to IT times just R1. That's 0.93 times 2 equals 0.86 volts. 1.8. Turn your ears on, Mike. Yep. Okay, so we've now got that voltage 1.86 across there. What else can we calculate? That's a volt drop. If you've got a voltmeter, put one terminal, one probe here and one probe there, that's what you would measure. What you tend to think of as this terminal sits at 20 volts. We've dropped 1.86 across there, so that terminal will sit at 20 minus between the two. Boy, you can't really do that. If you think about it, what would you need to know to calculate I2 and or I3? Which voltage? Voltage don't come out of anything. But you've got the volt drop here. Yeah. To do these two currents, we need to know. We know the voltage across these two is the same because they're in parallel. So that V2 is also across that resistor, but we don't know V2. So we can't isolate that resistor and that resistor yet, can we? We don't know enough. We know, what we do know is all of this current splits here, but comes back there, and we know the total of those two. We know the total resistance of those two, and we know that all of this 0.93 amps goes through the total of those two resistors. Do you get that or not? Some of it goes that way, some of it goes that way, but all of it travels through this 4.5 ohms equivalent. Remember, I told you, you calculated that equivalent resistance. It's like saying going to take those two resistors out and put a 4.5 in there. Yes, that'll give you the voltage. That's what I'm saying. So we can do V2 is equal to IT times R12, the R23, sorry, the combination of those two resistors in parallel, because all of that current has to go through that tool. So that's 0.96 times 4.5. My memory's not as good as I thought it was. And that comes out as volts. Yeah. Okay. And lastly, so this is 4.105. I can't do that. Yeah. We might as well finish off the voltages. V4 is IT 4 0.93 times 15 13.5 volts. That's 4.185. That's 1.6. Now so I1, I called it I1 or I2? I2 is equal to, this is where a lot of people do wrong, I2 is equal to, it's got to be this voltage. So many people at this point in exam questions at the foundation degree use the 20 volts. I don't know. Currents. V2 over 4.85 divided going to make much difference. And the resistance of R2 is 3 4.16 over, is it 2 ohms? I think the answer to that is and the is add them together 0.2 Near enough. Right? Yeah. Right, now, I hadn't mentioned this before today, but again, I'm not going to labour on it too much. The topic in the science, but at any instant in time, the algebraic sum of all the currents at a junction on a network is 0. We try not to think of it like that. I like to think of it as putting all the currents going into the junction on the left-hand side of the current law equation and all the currents leaving on the right. So in this case, I1 is going in, I3 is going in, and I5 is going in. So left-hand side of I1 is I3 plus I5, and then with I4 leaving and I2 leaving. I2 plus I4. We can then rearrange, if we want to find I5, we can rearrange that equation then calculate the unknown current. So what it is if you know all but one current junction, okay, alright, happy? Yeah. Remember how to go at that time? Simple problem. Alright, we'll do this. I1 is 10 amps. I2 is 65. And I4 2 amps. Write your Kirchoff's current equation for the two junctions A and B. So at A, what currents are going in? I1 plus I4, and the only one leaving is I3. Therefore, I3 is equal to I1 plus I4, which is 10 plus 2 equals 12 amps. Yeah? And then at B, currents going in are I3, I5 equals I2. Yeah. No, can't. No, it's I is equal to I2 minus, which is 16.5 minus. Right. And then lastly, you're all up to speed. Lastly, Kirchoff's voltage law. Who said that? No, you don't like her. Different than the currents because it's this any loop thing. Yeah. If we look at a circuit like this, there are the Kirchoff voltage law. The second law states that at any instant in a closed loop, so one single loop, any loop you've got where you've got a complete circle, doesn't have to have a battery or a source in it. They'll all comply. The algebraic sum of the EMFs or sources acting around the loop is equal to the volt drops. So what it's saying here is if we take the outside loop C, what we tend to do is put arrows on the components and the sources. So the arrow on a source goes with the point towards the positive terminal. And the arrow on a volt drop goes against the current flowing. So the source goes with the current flowing, volt drops go against the current flowing. And you must be strict with that convention. So we got current would flow up here, and would go down there and round that way, and that's the arrows. And then to write the equation, so if we take loop A, that's this loop, clockwise arrow, and on the clockwise arrow, V1 and V2 on the other side of the equation. We've got a loop here, where we've got one clockwise arrow, two, and clockwise arrows V3 and V4, so we could calculate V2 as equal to V3, rearrange it with the others. And then lastly, we've got the loop all the way around the outside. We've got one clockwise arrow again, E1, and then we've got V1, V3, and V4 as anti-clockwise arrows. Is that any help, Regan, or not? Yeah? Yeah. I mean, yes, it can get more complicated than that. You know, probably next week we'll be looking at circuits where there's more than one source in it. Alright? And on the next page, the example problem for the network shown, use KVL to determine the voltages V1 and V3. So if we look at that, the loop A, what we got going clockwise, E is equal to V1 plus V2. Therefore, we know V1 and V2, so V1 is equal to E minus V2. That is 12 volts minus 8 equals 4 volts. So we can now write 4 volts on there. We know that answer. Yeah. Here, we could now use the outside loop, because we've only got one unknown in that, because we now calculated V1. Or we could use this blue loop here to calculate V3. So let's use the blue one. Loop B, clockwise V2, anti-clockwise V3. We want to plot V3, so V3 to V2 minus V4, which is 8 minus 2. One thing that hasn't really been pointed out, I think I did in the science, and that'll pretty could crop up when you start doing problems with more than one source, as your current arrows on the way you're expecting them to go, and actually when you do your calculations they're not the right way. So what I'm saying is, if you get a negative answer to these problems, doesn't mean you got a wrong answer. It means either if it's a voltage, the voltage arrow has been assumed the wrong way. As a current, the arrow has been assumed to be the wrong direction. Okay. So, drink 10 minutes, 10 past, good.